In this problem, we have the Henderson-Hasselbalch equation that we're going to use for a problem where an HF solution, I guess, has been measured, 15 grams of it, and we've added 21 grams of sodium fluoride to that, and dissolved it in 750 mils. Now, just to kind of say at the outset, typically this is in a solution instead of in a weight. But that's beside the point. If you had a question where they gave you the grams of both the acid and its conjugate base, we can use the Henderson-Hasselbalch equation because that's what we're looking at here. This is the conjugate base, which we'd equate to the sodium fluoride, and this is the original acid, which would equate to the HF. So we're going to use this equation to solve this problem. So let's do it. So the first thing is we want to change this to molarity. So we'll have to get to moles. So to do that, we're going to have to take these grams and using the molar mass, go to moles. So I'll just start 15 grams of HF, and if the grams is on top, we know that I need to use the weight on the bottom to cancel the units grams. So I'll put the 20.01 without units on the bottom, and of course 1 mole on the top. So we can take our calculator and divide that 15 grams by the 20.01 grams in 1 mole. So this will give me roughly 0.750 moles. But of course we need to divide that by the volume, that's 750 mils. So it turns out then that'd be 0.750. If we divide by the liters in mils, we have to convert that to liters. So it'd be dividing the mole amount by the liter amount. We can then have the molarity of HF is equal to about 1. And we can do the same thing with our NaF. We're going to do the same thing, converting the grams to moles and then moles to molarity. So 21 grams of NaF. Again, I'd have to make sure my molar mass, I put the 41.99 on the bottom. That's to 1 mole. This will give me the mole amount, and then I'll again divide by 0.750. So let's take that 21 grams, divide that by 41.99. We get 0.500 moles roughly, and we divide that again by 0.750 liters to get molarity. So for that, dividing it by 0.750, we get 0.66, we'll say 7 here, 0.6668, but we'll round that up to 7 molarity. So now we're ready to plug in to this equation because we have the conjugate base's concentration, we have the original acid's concentration. They give us the Ka, and we'll be able to take the negative log of that, add that all together, and they'll give you your pH. Now I just want to mention something at the outset. The only reason we can do this, I guess, assumption that in water A- is really just the molarity of NaF, and the molarity of HA, our acid, is just the original HF concentration, is because we have a very weak acid and a weak base. There is not much dissociation of the HA to make more A-. There's not much, I guess, formation of HA from the conjugate base, so we can assume these are pretty much near the concentration we started with at the beginning, because again, it's a weak acid, weak base. Alright, so let's plug in and go, and I'll leave it at the math for you to do. So we'd say the negative log of, I'm going to put the Ka value, 6.8 times 10 to the minus 4th. We would take the negative log of that and add to it the log of our 0.667 divided by, and you can do this first, of course, divide the 0.667, that should have been NaF is our concentration, and divide that by the 1. So it's really just 0.667. I should have just had that in the molarity terms. So I just take the log of 0.667 and add that to the negative log of 6.8 times 10 to the minus 4th. Now I want to go ahead and leave that to you because from here on out that is math, and see what you come up with. That's it. Bye bye.